Hi everybody. All right, another video today about, we're moving towards the simplex method. We won't fully be able to get there in this video, but we will cover some of the more important details of why we need to do this, why we need to transfer to a matrix method, and how to set up that matrix method before we go over the sort of minutia of how that method works. The idea that we had from before on exam 2 was that we could graph a feasible region solution, and it was shaded in. It was really nice. But we saw that really only the corner points mattered in the end. And so if we want to talk about corner points of all of our regions ended up being solutions to systems of equations. Isn't that how you found these places? Right? If they weren't on one of the axes, right? We actually had to set up a system of equations and find those corner points. And so if we're going to do that anyway, rather than set out a full list and find all of the corner points, why don't we set up a matrix method that will find the corner points, and it'll do so in a way that we don't have to find every single one of them before we get to the optimal solution, right? That would be a really nice method to have. That method is called the simplex method. And to do that, we first need to take this idea of a region that's shaded and turn it into a big system of equations. Right? So let's start working on in that direction now. Right? Inequalities are really just nasty to work with, right? Even on a regular number line with one variable and one variable only. If I wanted to take this inequality, x is less than or equal to 10, and graph that solution, right, I could do that, right? But do you see how it would require me to shade in part of my number line? Well, that's not super great. I mean, I can do that, right? But what if I had two variables? We already saw inequalities with two variables and how we had to shade on Desmos, or it ended up being a little bit messier than we wanted. But what if we had 3 variables, 4 variables, 10 variables? Right? The methods that we have for inequalities very quickly get out of hand. They're much harder to keep track of. And I can't rely on the visual nature of the graphing method that we had before, right? It's inherently visual. And humans can't visualize things in 2 or 3 dimensions very well, much less 8 or 9 dimensions. Right? I don't think that's a really reliable indicator of a good solution method. So what we'll do is we'll trade a little bit of complexity in the form of more variables for the messiness of the trying to graph the solution. Here's what I mean. If I take the same inequality, x is less than or equal to 10, and I instead represent it like this, x plus y is equal to 10, right? That would essentially tell me, okay, any variable x in the previous region, right? Any x variable I had before, well, let this y variable, I got this sort of, represent everything after the x but before the 10, right? That's the slack, right? And so if I have x plus y equals 10, that's something I can actually work with, right? I could graph a line in 2 dimensions, right? But again, the whole reason we're doing this is to get away from the graphical ideas. So I won't do that, right? But you can see that introducing a second variable made things a little more complicated, because now all the different x and y pairs, right? I know they represent a straight line in 2 dimensions, but there's lots of different ways I can work with a line that I can't work with a picture, right? We already saw matrices work with straight line equations. And so, okay, maybe that's not so bad. Anytime I see this less than inequality, which we have a lot when we have our maximization problems, I'll introduce a new variable for each one. Right? So maybe I'll have 2 variables in my system of equations, but maybe I'll have 3 or 4, right? Or maybe more. The idea is that the slack is captured within a brand new variable, and I'd rather have more variables than deal with the messiness of shading a solution. I mean, we'll call that a slack variable, right? We'll make it a little bit more formal in a bit. All right, so here's our example, right? So adding more variables, it does increase the complexity here. But we have matrices to deal with big systems of equations. Remember when we did the Gauss-Jordan method on exam 2? Yeah, it was a little bit unwieldy, but the Gauss-Jordan method was nice because it always worked, right? As long as we didn't have this weird situation where we had, you know, the lines directly on top of each other or parallel lines that never intersected at all. The Gauss-Jordan method was good at finding the solutions, and yeah, it'll involve fractions most of the time, but that's all right. Right? We've got calculators to help us with the arithmetic. But finding the special ones and zeros may always work. And so, yeah, I'll deal with a larger system as long as I can deal with a system of equations. And so let me take this trick. So let me do a real quick graph here before I run away from the graphical method, just to remind you of what this looked like in the graphical method. X1 plus x2, right? We used to use variables like x and y for our systems of equations, but now because we're going to have so many of them, I'm going to put them all together. I'm going to call them all x, but because I can't use the same letter to represent multiple quantities, I'm going to give them a number: x1, x2, x3, etc. Right? You can think of the little number, the subscript, that's a name tag, right? You can't see it because my camera's so low, right? You can think of it as just like, hi, my name is X number 1. Right? That way I can use the same letter multiple times. Right? I'll be reusing lots of letters in this, right? Usually X and S, right? But I'll be reusing those letters and giving them name tags to help me keep them straight. So in my graph, this will be the X1 axis, and this will be the X2 axis. Right, instead of the X and Y axes. I'll give you a really quick sketch, right? Just back of the envelope. X1 plus X2 is equal to 20. Gives me intercepts of 20 and 20. And it's a roughly 45-degree line. Right? Again, I bet you if I check that with my ruler, it would not be anywhere close to 45 degrees. It's just a quick sketch. X1 minus X2 equals 14. So when X1 is 0, X2 is -7. Right? I can't even go down that far. -7 might be way down here. When X2 is 0, X1 is equal to 7. 7. Oops. No, X1 is equal to 14, excuse me. I looked at myself a little bit funny because I thought, that doesn't look right. I would normally tell you if you were sitting in the class, stop me if I make that kind of mistake, but I'll have to stop myself. So if you ever see me cut awkwardly and seem to jump around in the process, I might have made a mistake and just edit it out. I'm going to leave that one in though. Nobody's infallible, so I like to leave in things like that to remind students, hey, and I'm not perfect either. And so don't think you have to get all this the first time and perfect every time. We're learning the idea here. Here's our second line. X1 plus X2 is less than or equal to 14. It looks like my shading should go towards the origin. I'm plugging in 0, 0 to verify that. 0 plus 0 is less than 20. Got it. 0 minus 0 is less than 14. So this one shades towards the origin, but towards the origin is actually above the line. And that's why I don't use the terms above the line, below the line. I need a reference point. And so I will always say towards the origin, away from the origin. And X1 and X2 are supposed to be greater than 0. So I should stick to the first quadrant. From all of that, it looks like this region is the correct shading region. Again, this was last week, week before kind of material. I don't want to spend too much time here. I just want to emphasize what it used to look like so that I can show you what it's about to look like when we change it. This is a region which had a couple of different corner points. And this is a two-dimensional region. Okay, this is two-dimensional. It's a little bit messy because I had to graph it. It required me to be able to see the picture to give you this region. And to describe this region, I had to draw you a two-dimensional picture. Let me do this now, but let me take each of my inequalities, turn them into an equation using one of these slack variables, those variables from before. I called it y on the previous slide page thing, but now I'm going to start using the letter s to describe my slack variables. So my first inequality is x1 plus x2, and because that could be less than 20, if it is, I'll let this variable s1 take up the difference. So once I take up the difference in this s1 variable, it is now exactly equal to 20 every time, right? Because if x1 plus x2 is equal to 10, which it's allowed to be, now the s1 variable is equal to 10 to make the total 20 always. Right? So now I've got three variables. I'll do the same thing to the second inequality. x1 minus 2x2. Now that's allowed to be less than 14, so I need a slack variable there too. But because the amount of slack in the second equation may be different from the amount of slack in the first equation, I'm going to have to use a different slack variable. I'll call it S2 to represent the amount of slack in this inequality. Oh, okay. So now I've got 4 variables. x1, x2, s1, s2. Just as before, I can't really represent the slack here. But the nice part is the method that we're going to, the simplex method, it assumes that everything is in the first quadrant. All the variables are positive anyway. So I kind of get that one for free. I have to write it down just to make sure that that's the case, because if it weren't the case, then I couldn't use the simplex method. But x1, x2 greater than 0 kind of comes for free. I don't need to change that one into an equation. Now, let me look at my slack variables. If this slack variable were negative, then I think that means that something's messed up, right? Because if the slack variable were negative, wouldn't that mean that I had some stuff minus a slack variable equals 20? Doesn't that mean that x1 plus x2, when you added them together, doesn't that mean they had to have been greater than 20 to begin with? That's not the situation I'm trying to describe. I'm trying to describe where I start out with something less than 20 and I add some slack to give me equal to 20. And so the slack should be on this side of 20. I don't want slack on the other side of 20. That will be as a negative slack variable, right? We'll look at that when we look at extensions to the simplex method. But for now, the basic simplex method, my slack variables should not be negative. So I'll notate that as well. And again, I don't need to turn that into an equation. The method kind of takes that for granted. So slack variables can't be negative. We'll check for this in our solutions. Every now and again, you'll get a solution where it says the slack variable should be negative, and we'll throw that solution away. Right? Or at least we'll avoid that solution. So this thing has been transformed from a two-dimensional system of inequalities into a four-dimensional, because x1, x2, s1, s2 system of equations. So again, we're making the trade-off, right? We have purposefully made the trade-off between more variables, more dimensions, and going back to a method that we actually understand a little bit better. The Gauss-Jordan method is what was the basis for the simplex method. So I understand that method. I would much rather deal with a longer Gauss-Jordan problem than start something big, new, and completely nasty. So that's how I prepare all of my inequalities. And for now, everything will be a less than inequality. Right? So we won't introduce some of the nastier examples, the gotcha trick questions this week. Right? Next week, possibly, when we look at the extensions of the simplex method. Right? Well, what happens if some of my variables are greater than? Right? We'll have to talk about that. What happens if my region is not in the first quadrant? We'll have to talk about that. But for now, everything will kind of live right here, just like it did on exam 2. This right next to the origin region. And it's really nice to have that. So here's that same graph that I drew up above. I drew it bigger. I drew it a little bit more accurately so that I can actually count on it. I don't remember if I actually used the ruler to get the correct angles or not. But this region had 4 corner points in it. And this picture has 6 corner points total. 2 of them you see are not this one and this one. 2 of these corner points are not part of my region, so I didn't really consider them before. But again, we're going to a place where we don't have a picture to help us. And so we need to find all of the different corner points of our matrix, of our region. They're going to be represented with matrices. This point was 0, 20. This point was 20, 0. This point was 0, 0. This point was 14, 0. This point is 0, -7. It'll still be there. And this point, I believe, is 18, 2. Now, normally we'd have to set up a little Gauss-Jordan system of equations to do that. I'm going to scroll back just to look at the system. I'll make sure that 18, 2 works. 18 plus 2 is less than or equal to 20. That's correct. 18 minus 2 times 2, that's 18 minus 4. That's equal to 14. Right, so just plugging that in to check for myself. 18, 2 is the corner point of the intersection of the 2 lines. So if I look at all of these corner points, what I have in common is that all of these corner points have 2 zeros in them. And I know it doesn't look like it right now, but I'll have to introduce those slack variables to start seeing the zeros otherwise. Remember, the slack 1 represented how much slack is there before I get to the first line, the equals 20 line. That's this diagonal line here. So some of these points are on the line. For example, this point is on the line. So the slack there is 0, right? There's no slack because it's on the line. Likewise, this point is on that line. So slack 1 equals 0. For all the rest of the, well, same thing here. This slack 1 is equal to 0 because it's on that line. All the rest of these points are going to have some slack there, right? Try plugging in the origin. If you plug in 0, 0, 0 plus 0 is equal to 0, but I need to add 20 more to get to the line. So slack 1 would be 20. Interesting. And if I did this point, 14 plus 0 is 14. I add another 6 to equal 20. Right? I need to just add however much I need to get to 20. Here the slack variable would be even more. S1 would be 27. That'd be 0 plus -7 plus 27 is exactly equal to 20. And remember, here's the equations I'm working with. X1 plus X2 plus S1 is exactly equal to 20. So let me fill in all of my values so far. 20, 0, 0, 0, 14, 0, 0, -7, 18, 2. So 0, 20 is on the line, 18, 2 was on the line, 20, 0 was on the line. 0, 0 had a slack of 20, 14 had a slack of 6, and a slack of 27. Okay. Now let me talk about slack 2. Slack 2 is how far I am from this line, right? The equals 14 line. Well, again, some of these points are on the line. So like this point, 18.2 is on the line. So there is no slack. S2 equals 0. Same thing for this point, S2 equals 0, and this point, S2 equals 0. They're on the line. That's the whole point. If you're on the line, there is no slack. Just to scroll back up, remember, I'm supposed to be doing x1 minus 2 times S2, x2, plus S2 is equal to 14. Okay, so 0 minus 2 times 0 plus 14 is equal to 14. I think S2 would equal to 14 here. Yeah. Remember, plug in 0 minus 2 times 0 plus 14 is equal to 14. Right? And this is another reason why I don't say above the line, below the line. Notice how the slack is positive when I'm below, right, the first line, and the slack is positive when I'm above the second line. Right? I don't rely on above, below the line. It's not a very good indication anymore. In general, the slack is going to be positive, right, when you are in the shaded side of the line, right? And it's going to be negative when you're on the not shaded side of the line. How about this corner point way over here? 20 minus 2 times 0, 20, plus, I need to get back to 14. So wouldn't the slack variable be negative 20 minus 2 times 0 plus -6 equals 14? Yeah, that slack variable is negative. Interesting. And let's see, one more. So up here, 0 minus 2 times 20, that's -40, plus, 40, I think I need to go out to 54. Either be 40 plus 14 more would give me the equals 14. I need to get back to the 14 line. Yeah, so slack variable will be 54 there. Interesting. So 0, 20 has a slack 2 of 54. 20, 0 has a slack variable of -6. 0, 0 has a slack variable of 14, 2. 14, 0 has a slack 2 of 0, 0, 0. And 18, 2 is slack 2 is 0. Notice how in this little table that I've made, this is kind of it's a little unofficial, but it looks kind of like the corner point list of table solutions I had from the last week. Right? Normally I would have like a z value in here somewhere and I'd say, I'd plug them all in, figure out which one's the highest. But notice how in all of these rows, in every row, there are 2 zeros. 2 zeros, and 2 not zeros. Every solution has 2 of the variables which have to be 0 in the corner points. What that means is that basically, because I had 2 inequalities, 2 equations, right, I can actually give you, right, the values for 2 of the variables. That's basically like setting up a system of equations. The other 2 have to float, but if I let them be something other than 0, then I'm not going to be on the boundary. Right? If I tested, right, I didn't put any points in here because I know that none of the points in there would be optimal. But the points in there would have slack 2 positive, slack 1 positive, x1 positive, x2 positive. All the variables would be positive, right? But they wouldn't be on the boundary. And we discussed last week how if you're not on the boundary and you're in the middle, you can never be optimal. Right? So if we're going to force ourselves to stick to the outside, we're going to force all of the things which are not at the corners to have 0 for all the other variables. And so I'm going to have 2 zeros and 2 not zeros. So this is a big list of solutions, 4-dimensional solutions in my table. And I'm just looking at interpreting them graphically in 2 dimensions just to show you where all this stuff is coming from. But ideally, this table is much more simple to deal with. Right? But not every solution in this table, right, is feasible. And what I mean by feasible is not every solution in my table actually solves the original system of equations that I started with, right? Where x1 and x2 were greater than 0, and where s1 and s2 were greater than 0. Sometimes one of those things will not work out. It just won't work. I will throw those solutions away. Those are called non-feasible solutions. So I'll write that out. That's what I'm measuring in this last column. Is this solution a feasible solution? Does it match all of the inequalities? And does it match all of the boundary conditions that we had before? It looks like 0, 20 is feasible, right? Because x1 and x2 are greater than 0, s1 and s2 are greater than 0. But 20, 0 is not. Do you see how in 20, 0, x1 and x2 are greater than 0, but s2 is less than 0. So that's not a feasible solution. I'm going to quickly go down the rest of my table here. Essentially, feasible in this situation means all the variables are positive or 0. I count 1, 2, 3, 4 feasible solutions and 2 non-feasible solutions. And if you notice, the non-feasible, I won't do it in red because that's too close to the color that I wrote with. The non-feasible solutions, 1, 2, are 20, 0, that's this one, and 0, -7, this one. Do you see how non-feasible solutions are going to be the solutions which do not touch my shaded corner region? Right? So this is a way that we're not going to have to draw the picture. As long as we can guarantee all of our solutions are feasible and make sure that every time we go to the matrix, we'll force them to be feasible, we can make sure that we're skating around the edge of my shaded region without ever having to draw a region, without ever having to shade it in. So this feasible solution idea is going to save us a lot of ink, right? After now, we should never have to draw another picture, right? But the idea is super important. I think it's really important to realize every solution to this system of equations, the 4-variable solution of system of equations, it represents one of the corners. And as long as all of my variables are feasible, my solution is feasible, then I can be guaranteed to be somewhere on the boundary of that shaded region for my system of inequality. And so I like this. So I'd like to stay feasible, right, if at all possible. So to help me do that, I'm going to scroll up a little bit. I'm going to introduce this distinction between what we call basic variables and non-basic variables. Basic variables in our matrix will be those variables that have the special ones and zeros. And non-basic variables may not, right? They may have zeros in them, they may have ones in them. But do you remember when we were doing Gauss-Jordan, we wanted our Gauss-Jordan matrix to look like this when we were done, that special pattern of ones and zeros. In this matrix, we can't do that fully because you see how no matter how I do it, there's room out here. I can't get a special pattern of ones and zeros out there because in Gauss-Jordan, I'm only allowed to have one of those special ones. We called it a pivot. I'm only allowed to have one of them in every column and one of them in every row. And so if I use up both rows with two pivots, I don't have room for any more, right? Anything out here would be junk in the sense that I can't guarantee there'll be ones or zeros or positive or negative or anything, right? They'll just be junk. Those will represent a variable of 0. So in this particular matrix, you notice how my pivot points are at x1 and x2. That tells me x1 and x2 are going to be taking a number value, not 0. Well, it may be 0, but the 0 will actually show up in the matrix. I'll show you that. S1 and S2 would not be, right? They would be forced to be 0 because they are not basic variables. They're non-basic variables. And so if I have x1 and x2 are allowed to be numbers, but s1 and s2 are not, it looks like that is the 18. No. That's the 0, 0. That's the origin point. That'd be 0, 0, 20. Oh, I'm sorry. That'd be exactly the opposite around. X1 and X2 are allowed to be not 0. S1 and S2 are forced to be 0. So that would be 18, 2. Right? Those numbers would show up in the matrix exactly like that. Right? And when I'm reading in the matrix, I can say, well, what is the value of x1? Right? There's the x1. That's the special one. Go to the end of the row. X1 is equal to 18. I can read it just like that out of the matrix. Here, what's the value of x2? It has the special 1. So I go to the end of the row. X1 is equal to 2. Or excuse me, x2 is equal to 2. S1 and S2, right, they will have other things in them. I mean, let me take a moment to get the actual numbers from the matrix, what they would look like. Okay, sorry about that. Now, there are fractions in this matrix, and that's okay. We're going to see lots of fractions, but we're going to have computers and calculators to help us with that. Okay? This is the actual matrix which represents this corner, right? This solution, 18, 2. Notice how the S1 and S2 columns are kind of filled with junk. Now, that doesn't mean I can ignore them. I still have to keep track of them. But because they do not have the special ones and zeros, right? There is no special 1 and 0 here. And so I don't have to read it out of the matrix. There's no special 1 here, right? So I can tell you that S1 is equal to 0. Likewise here, there's no special 1 in this column. So S2 must be 0. It's a non-basic variable. So where the special 1s are, they tell me that I'm dealing with basic variables in these columns. And where the special 1s are not, they tell me I'm dealing with non-basic variables. Some textbooks and some questions on your homework, right? Because I didn't code every single question on your homework. Some questions on your homework require you to actually label the rows. And they would be labeled like this, right? Because in row number 1, the special 1 appears in this column. That's the x1 column. I would label the entire row as the x1 row. And in the second row, here's the special 1. That's in the x2 column. I would label this entire row the x2 row. For homework questions that I code, I don't make you do this because if you know how to read the special ones, you never actually need to write that down. You can see it anytime you need it, and forcing yourself to write it down every time is going to be, it's just more steps, I think. So I'll draw your attention back to it when we need it, but I won't make you keep track of it because the rows are going to change. The columns will not change. I label my columns because the columns should never change. It's always x1, x2, s1, s2 in that order. And the right side did not get a label because that's just a number over there. Some homework questions will require you to write something like TOT, like the total. On the questions that I write, I won't require you to label the right side of the matrix, but some of your homework problems will. I think I've put a little text there to remind you, oh, hey, this one, you need to write TOT. It's just a difference in style, that's all. When it comes down to it, I've got basic variables and non-basic variables. And notice that when I've got my basics and non-basics, I can check, is this a feasible solution? Is x1 and x2 greater than 0? Yeah. Is s1 and s2 greater than 0? Yeah. All of my variables are positive, so this represents a feasible solution. A feasible solution because all of my variables are positive. I believe if you were to search on the internet, you might find some textbooks call this a basic feasible solution. So I'll make sure to call it that as well. You might hear it called BFS. But be very careful when you search the internet for Simplex method help. I don't want to set myself up as the only person in the world that can show you how to do this, but a lot of times other classes that cover this topic may be much higher theoretical classes. I don't want you to find some like really dense textbook talking about the Simplex method and think, oh my God, I need to understand all of this. We're just scratching the surface with the Simplex method. And so post in the forums, right? Send me an email, ask me a question, right? Definitely get in touch with me because yes, we will have to know a lot of the details, but not all the details. And so I can help you sort out, right, when that is. And that's part of why I'm doing these videos. It's taking a lot longer for these videos because I know that it's really hard to find good help when it comes to Simplex method. So we've got basic and non-basic variables, which gives us feasible solutions or non-feasible solutions. Okay, I feel like we're really on the cusp of a really great method here, right? Because if all of my solutions are corner points when they have zeros and non-zeros in these special positions because of the matrix, I feel like all I need to do is figure out which one of these corner points is best. That's what we did in the corners method anyway. Right? The matrix method we're about to introduce, the Simplex method, helps us figure out which one of them is best and how do we find it. So let's scroll down. Oh goodness, right? So you see a big flowchart coming into view here. Ignore that for just a moment. Right? The Simplex method, right, underneath all of it, is just a big matrix method for how do we find the corner points which optimize my problem. Right? Remember when we were solving things on test 2, we had maximize z equals blah, 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 given a big system of inequalities. Well, we just talked about how to change that big system of inequalities into a system of equations. We saw that all of those equations represented corner points with the special ones and zeros, basic and non-basic variables. All we're doing is just moving between them. Right? I need a place to start, and I need to know how to move between them. That's all this is. And yes, it looks really complicated, right, in this flowchart. And that's because this flowchart is going to represent several weeks worth of our topics. Right? This flowchart, I believe, is 3 weeks worth of class. So don't think you have to know every piece of this flowchart right away. Right? Certainly, we haven't even scratched the surface. Right? We've only just introduced the simplex method, right? Not much less how it actually works. Right? In general, right, if I were to give you a rough outline, this part of the flowchart is week number 1. Right? This part of the flowchart is week number 2, roughly. And this part of the flowchart is week number 3, roughly. We'll mix and match a little bit from all the time. Right? And so, again, don't feel like you have to know everything about this flowchart right away. This flowchart, by the way, is posted on my Open Math. You'll have to scroll down into unit number 3 under module, I believe it's module F, right, to download a copy of it. And I really like flowcharts, right? But again, I don't memorize them, right? It's good to see it, right? But once we understand why we're doing what we're doing, we don't need to look up this flowchart like an encyclopedia every time. Yes, I kind of made that flowchart from my understanding of the simplex method. So I kind of knew that flowchart was the way we need to flow through the process, right? But when you make your own little flowchart, it might not have this many steps, right? Maybe you'll make something like this for your exam, and it'll be a little bit shorter, right? And you'll be able to omit some of the words, right? Because you understand, you say, okay, well, first you do this, then you do this. It doesn't have to be so complicated. This is just my first draft of getting a decent process on paper. Again, it's posted in my Open Math. So let's set up the simplex method. So the closest thing we're going to get to a list of steps this week. Okay? We've already done most of them. Right? Step 1 is change. Oops. So you change inequalities to equations. That will involve the slack variables. So that whole thing with the slack variables, that's part of step 1. So maybe we'll have 1 inequality, maybe we'll have 2, maybe we'll have 3, 4, or 5, I don't know. We'll just introduce more and more variables until we don't need any more. Right? Some of the problems you'll find, yeah, we're going to have 5 inequalities and 3 variables. And so you'll have 5 slack variables from the inequalities, plus 3 more regular variables, plus 1 more that we'll introduce in step 2, right? Maybe we'll have a matrix with 9 or 10 columns and 5 or 6 rows, right? Ugh, nasty. Again, we're going to have computers to help us. I'm going to show you how to do that without breaking the bank and without buying like 17,000 pieces of paper. I'll change all those inequalities to equations, right? I won't say change. We're not really changing the objective function. We'll format the objective function in a way that could go in our matrix. Remember, our objective function, right, usually looked something like this, right? Z equals x1 plus 5x2, and we were maximizing this thing. But our matrix had x1, x2, s1, s2 all on the same side. And I'm going to put z on the same side when we go to the simplex method. And then the numbers on the other side. So do you see how the objective function doesn't always go directly into the matrix? Right? I'm going to force you, right, because the method's going to force you, but I'll say I'm forcing you to always make z positive. Right? So z is equal to 1 there, right? Because it's 1z. The matrix only brings out the coefficients. And so if I were to force myself to have z to be positive and on the left side of this equal sign, I would have to move the x1 to the left. It would become -1 x1. I have to move this 5x2 to the left, and it would become -5 x2. I wouldn't have any s1s and I wouldn't have any s2s, so I'd make them 0. And when I did all of that, it would be equal to 0 because there would be nothing left on the right side of that equal sign. And so what you'll see is that's step 2, is basically format the objective function. And when I post these OneNote links on Blackboard, I'll actually move this around. I'll write a few more steps so that this will be a little bit better formatted on the OneNote that you read. But for now, I'm just going to move that out of the way. That is step 2. Format the objective function. Okay? And so you'll see I've got a bunch of negative numbers there. And so step 3 is to collect all of that into a simplex matrix. And the textbooks will usually call this a simplex tableau. I mean, the French word tableau, it sounds very fancy, right? We know that that means matrix in this class. So I want you to think about this as a big matrix. I'm going to say tableau in future videos, and I'm going to say tableau on your homework, right? Because a lot of times, to see the inner workings of the matrix is a little bit much for a lot of people, right? So there are a lot of theoretical details that the matrix is hiding from you. But we don't need to understand all those details. All I need you to understand in this class is that it is a matrix, and all of the solutions represent corner points, right? And I'm going to teach you how to transition between those corner points in the next video. And in the later parts of the homework this week, you'll do the same thing, how to transition between them. And we need to start with a basic feasible solution. So I can't go into the simplex method and start working with it until I can be sure that we start with a basic feasible solution. Remember, that means that I have all of my inequalities being satisfied. All of my variables must be positive. Okay. And so we have less than or equal to inequalities to start with. And when we changed them in step 1, they became equations. And there were positive constants on the other side. So basically the numbers on the right side of that bar, they should be positive. If they were negative, then that would represent a greater than, and that's not something we're dealing with this week. So we have equations with positive constants, and we have all of my slacks and all of my variables are greater than or equal to 0. Because remember, my variables shouldn't be less than 0. Right? Most of the time, those were reality variables anyway. Right? And my slacks can't be less than 0 because, again, that would represent a greater than type inequality. We're not dealing with that this week. So we'll guarantee that we start with a basic feasible solution. And here's the good news. Right? In the standard maximization problems that we're going to start with this week, this will almost always be the case. We'll start at 0, 0, and so the slack will be positive to all of the lines because 0, 0 is right, on the shaded side of all the lines. Right? So step 4 will be an afterthought for this first week. Right? Yeah, I'll say it. Yeah, I will check it. But, it won't be a problem until next week or maybe the week after. But we'll always make sure we start with the basic feasible solution. Step 5 and beyond, we'll deal with it in the next video, because that's basically how does the simplex method work. We're just working on setting it up here today. I went back up above and I copied over our first example, and I've got my objective function and all of my inequalities from before. We're going to make this into a simplex method matrix tableau, right, to end the video. In step 1, all of these inequalities became equations with slack variables. x1 plus x2 plus s1 equals 20. Notice how it's always an equal sign after I get rid of all the slack. x1 minus x, or minus 2 times x2 plus s2 is equal to 14. So that's step 1. Done. Make all of your inequalities into equations with slack variables. Step 2 is now format your objective function in such a way that it can go into the matrix. And I apologize, the objective function usually goes at the bottom. So I'm going to put it at the bottom. And that would be minus x1 minus 5x2, because remember, I moved them all over to the left side of the equal sign, plus z equals 0. So now I've collected my inequalities and my objective function. Remember, we get these for free. It's a good idea if you also add these things, or the slack variables are supposed to be positive as well. But now let me go to a matrix. This matrix will require, let's see, 1, 2, 3, 4, 5, 6 columns, right? 1 for every variable plus 1 at the end across the bar. So 6 columns. And it will require 1, 2, 3 rows. 3 rows, 6 columns. I'm going to label my columns just to help me out. Bar. And now I fill it in. Remember all of the coefficients from my system of equations. There we go. I put it there. So this is basically my full system of equations that I'm transforming into a matrix. 1, 1, 1, 0, 0, 20, 1, negative 2, 0, 1, 0, 14. Right? Notice how all the variables which do not appear in these equations, they get zeros. The first equation has S1, the second equation has S2, the third equation is going to have a Z. Negative 1, negative 5, 0, 0, 1, 0. So you're allowed to have a 0, right? Even though if it's not a basic variable or any of that. This is my simplex matrix. A lot of textbooks will actually go out of their way to write another line down here on the bottom. I'll match that. Because they want to emphasize the fact that this last row, this represents my objective function. It's special, right? And this 1 here is even more special. That 1 will never, ever, ever be touched. So that last column and that special 1 in that very bottom right-hand position will never change. Right? I know it seems a little bit wasteful to write an entire column in your matrix, which will never change. Right? But this represents the objective function, and if there's not that special 1 there, I will never be able to read the solution for the objective. And the whole point of this problem is to maximize the objective. What's the point of doing any of this if I can't figure out what Z is? And so I always have to have that special 1 there in that position. This simplex tableau is a good place to start. It's got the slack variables, right? It's got positive constants on the right-hand side of the bar. It's got a bunch of greater thans. I've got all of my technical details in a row. And this solution is feasible. remember, to read the feasible solutions, for every row, I look for the special one, and then I go up to the variable. So S1 is a feasible or a basic variable. S2 is a basic variable because it has a special one. Z is a basic variable. It always will be a basic variable. X1 and X2 are non-basics. So to read this solution, X1 is 0, X2 is 0, S1 is 20, follow that to the end. Right? S1 is equal to 20, S2 is equal to 14, and Z is equal to 0. Right? It has that special one too, right? But right now, Z is equal to 0. This is a feasible solution. Or a basic feasible solution. I'll use the abbreviation from earlier. This is a basic feasible solution. And so I am allowed to start the simplex method from this position. Any basic feasible solution is a good candidate for where to start the simplex method from. And next week and the week after, we'll learn that the 0, 0 position won't always be it. But for our basic maximization problems, it will be. And so this 0, 0 position is a good place to start the simplex method from. And this matrix, right, with all of the wonderful technical details behind it that I won't always write, right? The stuff in this video, the marking the basics and the non-basics, marking down what the solution is every time, I won't always do that. Right? But it's always in there. You can always read the matrix to find those things. Right? Because where we're going, we're going to have to be writing so many matrices that we don't have time to write all of that detail every time we have a matrix. But this is a good position to start the simplex matrix from. And so now I will take this matrix into my next video. So the next time you see a video from me, I'll start from this matrix and I'll solve it, right, using the simplex method. Have a good one.